Hi and welcome back to this second part of chromatography. In this video we're going to look at column chromatography and then how this has been improved upon for the use of high performance liquid chromatography. Okay, so again a reminder that chromatography always uses the same principles. It separates a mixture of compounds based upon their affinity for a stationary or mobile phase, which will be determined by the intermolecular forces / the polarity and size of the molecule. Okay, so a non-polar phase will have a greater affinity for non-polar molecules, and polar molecules will have a higher affinity for a polar phase. That phase can be either the stationary phase or the mobile phase. When we read questions, we really need to pay attention to the polarity of the stationary and the mobile phases so that we can understand which components will be spending more time with which, i.e. which will move slower and which will move faster. So with column chromatography, we are essentially taking the same thing that we saw with TLC and paper chromatography, and now instead of it being a thin layer on a solid backing, we are taking that fine-grained solid and packing a glass column with it. The mobile phase is going to be poured into the top of the column now and will be gravity fed. Okay, so instead of being pulled up by capillary action, gravity will cause the solvent to flow through the column packing, which is going to usually again be silica gel or something like that. We will load the sample onto the column bed. We let it run in a little bit, then run the solvent onto the top. As the sample moves through, it separates out into its components based on the absorption between the component and the stationary phase. The most strongly adsorbed, i.e. the one most attracted to the stationary phase, will move the least, and the one that has the strongest affinity for the mobile phase will move the most quickly through the column. These will then move out of the column and elute out the end, so we can actually collect these in test tubes and then use this to purify a mixture of compounds and determine which fraction has the compound we want and keep that for further processing or multiple steps in a synthetic pathway. So the time taken for each component to leave the column is referred to as its retention time. Okay, the smaller the retention time, the faster it has passed through, the higher affinity for the mobile phase. Essentially what we're seeing in a column is that we have an inert solid that is often coated with something, and this forms our stationary phase. Okay, and then our analyte will run through and adsorb to the stationary phase. This is an example of a gas chromatogram where we have a stationary phase which is small particles coated in a high boiling point liquid, usually a hydrocarbon, and the mobile phase will be a gas. The analyte is usually introduced in as a gas as well and produces the mobile phase. So the solubility of these compounds into either the liquid that forms the stationary phase or the gas determines the separation. All of these, however, work on surface area and increasing the number of adsorption-desorption events. With paper chromatography and TLC, if we want to get better separation, we need to allow it to run for longer. We do that by increasing the length of the piece of paper that we allow the sample to run up. With a column, we can increase the length of the column, therefore providing more packing that the sample needs to travel through in order to get off the column. With HPLC and gas, again, we can increase the length of the column or change the particle size of the packing, increasing the surface area, i.e. decreasing the particle size of our solid phase packing material, increases the number of adsorption-desorption events, therefore increasing separation of our components. So we take this idea of column chromatography and we can mechanize it. This means that we place our stationary phase, again a fine-grained substance, okay, for a 20 centimeter column, it's fairly standard, and this means that we have a column. This will be packed with our stationary phase, and then we have a pump which under pressure pushes the liquid mobile phase through our column. We will inject our sample onto the column through the flow of the mobile phase. This is generally done under pressure because with such finely, tightly packed stationary phases, as we try and force a liquid through this, we get back pressure. So this will usually be a pressurized system. And then the sample will move through the column. In these, we can't see what is going on in the column. So the eluent, or what comes off the column, passes through a detector, usually a UV detector for organic compounds, and there is a recorder which will record the chromatogram. Because we don't see dots on this, we can't calculate the retention factor based on the solvent front and the dots. What we need to use is the chromatogram, which will measure the time and tell us how long a component took to come off the column. So with high-performance liquid chromatography, it's used for substances that can't be separated using heat, like proteins, because we can do it under mild conditions, organic compounds. Okay, it's used as a separation technique for both qualitative purification and quantitative to quantify how much might be present in a system. It is very, very sensitive. It is done with very small particles. High pressure needs to be used in order to push the mobile phase through. When the sample isn't polar, we can assume interactions with the stationary phase are dispersion forces only. Okay, therefore, eluted components will appear in order of size, being the smallest first, because the smallest will have the smallest amount of dispersion forces, therefore the least interaction with the stationary phase. Okay, this also means that alkenes will come off before alkanes, which come off before esters, alcohols, and carboxylic acids, depending on the polarity of the stationary phase and the mobile phase. This is what a HPLC chromatogram usually looks like. If you have humps here, what we're seeing is non-clear separation. Okay, here we have a clear separation of the components. Here we haven't. So you may want to increase the length of the column, slow the rate down, or things like this. What we do is the position of the peak gives us the retention time. This is much like the RF that we saw calculated for our TLC, but this is the length of time that it spends on the column. You'll notice here it goes from 0 to 4 on this chromatogram, so this fraction eluted after 4 minutes. This is the time at which it's detected, and it's the corresponding position of the peak in the chromatogram. Retention times will be the same for the same compounds run under the same conditions using the same mobile and stationary phases. This allows us to identify mixtures or compare to standards. The area under each peak is proportional to its concentration. So this is a gas chromatogram of a petrol sample, and we can see here that we have our retention time starting at 0 up to 20 minutes. These will be smaller. It has a lower retention time, so these have come off the column earlier, so they will be the smaller compounds because they had less dispersion force interaction with our stationary phase. And then our larger compounds are going to come off later. In fact, this one here is indicating that this number of carbon atoms is 4. These are compounds containing 5 carbon atoms. Then we see compounds containing 6 and 7 carbon atoms, remembering that petrol is a mixture of different hydrocarbons. What we can do is we can run a chromatogram of a reference sample. So in here we can see that we have butane, 2-methylbutane, hexane, benzene, and 2-methylhexane. Comparing this to a chromatogram run under the same conditions, we can then identify the components that we had in the mixture. In this case, the retention times correspond to the peaks that are labelled here, 1, 2, 3, 4, and 5. With concentration, HPLC instruments are accurately calibrated using standards. What we do is much the same as we talked about in Year 11. In order to determine the accurate concentration of a sample in a HPLC, we must first create a calibration curve. So we prepare a series of standards of known concentration of the sample of the analyte that we're looking for, run each standard solution through the machine to make a chromatogram and determine the peak height. We plot the peak heights versus concentration to get a calibration curve, and then we run our sample through the machine, match the peak at the retention time, measure its area under the curve, and interpolate the value for the concentration from our graph. So this is what it would look like. These would be separate runs run independently with increasing concentrations, 9, 10, 11, 12, 13, 14%. So this would give us our calibration curve as plotted here. Then we could say take a sample of white wine, measure the peak at the same retention time under the same conditions, take its peak area and read off the corresponding ethanol concentration, which here would be about 9.25. In the case of the red wine, the peak height would correspond to a higher concentration of 11.6%. So we can use this to quantify the amount of something as long as we are able to produce a calibration curve. So let's have a look at a couple of sample questions. This one says a series of standards of ethane were run through a chromatogram, followed by a sample of unknown concentration, yielding the results below. Plot a calibration curve and determine the concentration of ethane in the sample. So we have a series of increasing concentrations versus peak height. So this is going to be our x-axis, and our peak height is our dependent variable, so this is going to be our y-axis. Peak height and area under the curve are proportional in HPLC, so we can just take the peak height. The sample has been given a peak height of 7. So what we're going to do is plot this to form the calibration curve, and then we're going to use the calibration curve in order to read off the concentration of our sample. So if we plot this curve, we can then go, if we had a peak height of 7, okay, which was the sample value that we were given, we would use a ruler to plot down, and we would see that the equivalent concentration would be 0.35 molar. Okay, we need to be very careful with your axis when drawing the graphs. Ensure that your independent variable is concentration and your dependent variable is the peak height. Also, do not force your graph through 0 unless you have specifically been given a data point for 0 concentration. Okay, so that will give you the wrong gradient and often give you a value outside what VCAR will accept as the correct answer in these questions. So another example from an exam question is giving us the plotted calibration curve. This one is looking at the mass of caffeine in a particular drink using high-performance liquid chromatography. 5 ml aliquot of the coffee drink was diluted, remembering that any time we have this, we need to remember the dilution factor to work backwards to find the original concentration. The sample of the diluted coffee was run through the HPLC, identical conditions used to create a calibration curve, and the peak area was found to be 2,400. We will go up to 2,400 using a ruler to accurately do this, read across the graph, and determine the mass of caffeine in the undiluted coffee, remembering that the value we get off the graph will be in the diluted coffee. Okay, and we have diluted it by a factor of 10, so we need to multiply by 10 to get the original concentration. When we do this, we should end up with these calculations here. So reading off the graph, we get a 0.04 grams per litre in the diluted sample. We're going to multiply this by 10 to determine 0.4 grams per litre in the undiluted sample. and then we had this in the mass of caffeine in 300 mils, so in 350 mils, so this is grams per liter. Okay, and then we're going to convert that to get 350 milliliters. So we would divide this by, if this is grams per liter, we divide by 1,000 and then multiply by 350 to get the final answer. Okay, again, many students overlook the dilution factor. Always look out for that word dilution in VCAR questions, because you will have to work back to the original concentration. That's it for this. I will do another video talking about ways that we can influence HPLC and looking at structured responses to describing how things elute differently in the HPLC. And of course, as always, we will look at some worked examples in class. Hope that's starting to make some sense, and I will see you in class.